Welcome to the deep dive. Today we're tackling autocorrelation. It's something you'll often run into when you're looking at data over time.
That's right.
We've got some great questions lined up to guide us.
Yep.
And our mission really is to get a clear handle on what autocorrelation is, why it's a big deal, and some ways to handle it.
Exactly. Without getting lost in all the super technical weeds.
We want to get you up to speed, but properly.
So autocorrelation, simply put, it's when data points collected over time are related to each other.
Okay.
Like, think about sales figures. Today's sales might be influenced by yesterday's sales, right? That connection over time. That's autocorrelation.
Right. And that's different from multicollinearity. I sometimes get those mixed up.
Yeah, good point. Multicollinearity is about correlation between different predictor variables in your model. Autocorrelation is focused within a single variable, or more technically, the model's errors, over time.
Got it. So it's about the errors having a pattern over time.
Precisely. The leftover bits after your model makes its prediction.
So what kind of data is most likely to have this issue?
Well, it's predominantly time series data.
Okay.
Things where the sequence matters. So stock prices, definitely. Economic indicators, maybe GDP growth or unemployment rates. Weather patterns, temperature logs, rainfall.
Anything sequential, really.
Yeah, basically anything where one observation naturally follows another and might influence it.
And how do people actually, check for this? Is there a specific test?
A common one is the Durbin-Watson test. It's designed specifically to detect autocorrelation in the residuals of a regression model.
Residuals, again, the errors.
Exactly. The test gives you a statistic, a number between 0 and 4.
And what do the numbers mean?
So a value close to 2 generally suggests no significant autocorrelation. It's kind of the sweet spot.
Okay, 2 is good.
Right. Values getting closer to 0 usually point towards positive autocorrelation.
Positive meaning, if an error is positive, the next one likely is too.
You got it. Like, if your model underpredicts today, it's likely to underpredict tomorrow too. And values closer to 4 suggest negative autocorrelation errors tend to flip-flop, positive then negative, or vice versa.
Okay, so seeing that pattern in the errors, that's the red flag. Why is that such a problem for, standard regression?
Because it fundamentally breaks one of the key assumptions of ordinary least squares OLS regression.
Which assumption is that?
The assumption that the error terms are independent of each other. Autocorrelation means they aren't independent.
Oh, right.
And when that happens, well, the standard results can be misleading. Your coefficient estimates might still be okay on average, but their standard errors can be wrong.
Standard errors. That affects significance tests.
Exactly. We'll come back to that. But yeah, it messes with reliability.
Now, I saw a mention of the partial autocorrelation function, PACF. What's that for?
PACF. It's another tool, mainly used in time series analysis. It helps you figure out the direct relationship between an observation and its past values, its lags.
Direct relationship. How's that different?
Well, imagine today's sales are related to yesterday's, and yesterday's are related to the day before. PACF tries to isolate the effect of, say, sales 2 days ago on today's sales, after accounting for the effect of yesterday's sales. It strips out the intermediate influence.
Okay, so it pinpoints the direct link to specific past points.
Exactly. It's really useful for figuring out the structure for models like AR models, which we can touch on.
That makes sense. Trying to cut through the chain reaction.
Yeah.
What about just dealing with it directly, using lag variables?
Yeah, that's a very intuitive approach. If you think past values influence the current value, you just include those past values as predictors in your regression model.
So predicting website traffic today using yesterday's traffic number.
Precisely. Or maybe yesterday's and the day before's. You add those lagged dependent variables right into the model equation. It directly accounts for that time dependency.
What happens if you don't do that? If you're forecasting and just ignore the autocorrelation?
Well, your forecasts likely won't be as good, possibly quite inaccurate. Because the model isn't capturing the real dynamics in the data. It doesn't understand how the past systematically influences the future, so its predictions are based on an incomplete picture. You might miss trends or cycles.
And that brings us to those AR models you mentioned, autoregressive models.
Yes. AR models are specifically designed for this situation. They explicitly use past values of a variable itself to predict its future values.
So the model structure is the lagged relationship.
Exactly. An AR1 model, for instance, uses the immediately preceding value to predict the current one. An IR2 uses the past 2 values, and so on. It directly models that autocorrelation.
Okay. And finally, you mentioned standard errors earlier. How does autocorrelation mess with those?
Right. This is a subtle but really important consequence. Autocorrelation, especially positive autocorrelation, tends to make the calculated standard errors smaller than they actually should be.
Smaller, so things look more precise.
Exactly. Which means your coefficients, your parameter estimates, might look statistically significant, low p-values, when they aren't truly significant if you accounted for the autocorrelation properly.
Ooh. So you could think you found a real effect, but it's just an artifact of the correlated errors.
Precisely. It leads to incorrect inferences,
Oh.
potentially bad decisions based on flawed statistical results.
Okay, let me try to wrap this up. Autocorrelation is about data points, especially in time series, being related across time. It's not multicollinearity.
Correct.
We can spot it with things like the Durbin-Watson test, understand direct lags with PACF,
Uh-huh.
and ignoring it is bad for forecasts and can make our results look better than they are.
That's the gist of it.
So we can address it using lagged variables in a standard regression, or by using specific time series models like AR models.
Absolutely. The key is recognizing that temporal dependence matters for valid analysis.
So the big takeaway is that when time is involved, the past often echoes into the present in our data, and we need tools to understand and account for that echo.
Very well put. And maybe a final thought for everyone listening. Think about how this applies beyond just data. How often do past events, decisions, or even moods influence what happens next in your own life or in the world?
Yeah, that ripple effect.
Right. Understanding these kinds of dependencies, even just intuitively, can give you a richer perspective on how things unfold over time. Maybe think about one example today where yesterday clearly influenced today for you. It's everywhere once you start looking.